Okay, we're on to our fifth lesson in parallel in electrostatics. And this one is applications. Okay? Thanks for all the coughs and waiting for us to start recording to get all those coughs going. Halls? Halls, anyone? It goes well with the donuts that are up front. Okay. So, applications now. We have all the formulas. We hopefully know what they do and what they mean and all the concepts. We're now just changing it away from a point charge, where we've done everything from as charges and radially away, to parallel plates. Okay, so we'll see what happens there. Parallel plates are large flat metal plates. They're charged up. So we have a positive charge and a negative charge applied to them. And if the plates are very wide and they're quite close together compared to how far apart they are, then we get a cool physics effect in there where the electric field, and I'll just draw the electric field here in, let's say, blue. The electric field will be not radial, but parallel. Okay, it goes from the positive to the negative as electric fields go. And let's say if we charged it up with 300 volts, we could say that the top plate here is 300 volts and the bottom plate is 0 volts. So what we're doing is getting not a radial E field, but a parallel E field. And a parallel E field is constant no matter where you are. It's kind of like a parallel gravitational field. So we have a parallel gravitational field right here in the classroom. It's all down. It's all 9.8 no matter where we go. And once we have constant E fields, or constant G field, as you know, some of the physics makes it easier. Some of the calculations that we do becomes easier. Let's just see, do I have these up? Yeah, here's a graphical interpretation of an E field. The lines go from one plate to another. Lines go to one plate to another as we go down. And the different colors are the different voltages as you go across. It goes from one voltage to another voltage. And so the changes in the voltages change across. Let's take another internet look. This is parallel plates that are actually dialable. So as you dial and turn this dial here, you can swing in these, and these look like Ds. When you look at from the side there, they're Ds, and these plates go in between the other two plates to increase the E field between them. As you dial in more plates that go in between different plates, you get different E fields, and you can see that if you search for electrostatics parallel plates, there's lots of these diagrams. E going down, positive to negative, and positive to negative, and the physics that occurs in between is quite easy to calculate. There's even actual, experiments where you can start seeing the E field actually in the liquid or in the iron, the shavings. Okay? And as you go down, you can just see all the different things. They're showing the large parallel plates with voltages on them, and then people actually constructing them and showing the actual physics of them, what's going on. So you can see how many diagrams there are. In applications. Okay. I like that one. It's kind of quite clear. When you get to the edges, it starts rounding out. So let's just take a little bit of a look here. Let's take an example. Let's imagine that we have plates separated by 5 millimeters and charged to 500 volts. We're going to make a graph of voltage versus distance from the lower plate, and we'll find the slope and analyze what the units of the slope have to mean. So basically, if the bottom plate is negatively charged and the top plate is positively charged, it goes from 0 to 500 in linear steps, and we're going to measure the distance in meters here, millimeters in this case. So we'll make a graph. At the bottom plate here, if we measured it, it would be at 0 volts. And at 1 millimeter, it would be, we'll say this is, I guess, 5 millimeters apart, right? It is 5 millimeters apart. So we're divided, that's 1 millimeter, 2 millimeters, 3 millimeters, 4 millimeters, and 5, we reach the other plate. We're going to have a point here of 100 volts, and at 2 millimeters, it'll be 200 volts. And you'll see that we get a direct relationship here, a nice linear relationship. We want to find the slope of that line. So the rise over the run. The rise is measuring what? The rise is measuring the height. No, the rise is measuring the voltage. So the rise is actually the change in voltage. And the run, the x-coordinate, is measuring the separation distance. So the units here is volt per meter. Now, let's just play a little bit with this. A volt per meter, sorry. A volt is a joule per coulomb. That was yesterday. A joule per coulomb, energy per unit charge, over a meter. Okay, just going to write it out again, just not as a fraction, with a fraction. So this will be, let's call it cm, coulomb meter. But if you kind of note something here, maybe you don't, maybe you can. What's a joule per meter? Yeah, exactly. This will then, that's a Newton, a joule per meter, because a Newton meter is a joule, so a joule per meter is a Newton. So this becomes newtons per coulomb. So a volt per meter is equivalent to a Newton per coulomb. What's a Newton per coulomb? E field strength. This is electric field. So the slope of this, I guess I got to spell slope correctly. The slope of this graph is the E field. Okay? So a volt per meter is our E field. Let's swing on over to our next page. So we find that for parallel plates, there's a constant ratio. So there's a constant ratio of the voltage drop over the distance. Why is it constant? Because it was a constant slope. And the ratio is the E field. And the electric field is thus uniform inside the plates. The E field is uniform inside the plates. And the electric field is given by the voltage difference over the plate separation. So the E field is given by the voltage difference over the plate separation. okay, where E is the electric field in newtons per coulomb or volts per meter, either one. We know it as newtons per coulomb though, and it's uniform. And the direction of the E field is always away from the positive and towards the negative. It's a pessimistic field. And the change in voltage is the voltage across the plates, the voltage difference from one plate to the next. And D is how far apart they are. Hence, when we start taking a look at some of these designs, let's take a look. I saw a massive one go by here. Here we go. Look at how many plates there are there and how close they are. Right? We want them closer so that we can increase that E field between it. And that one that I had turned around, look how close those are. You can't even fit a piece of paper in between them. And they're not touching. Right? You want them very close. So, let's try example number 2 here. Find the electric field and the direction inside these plates. Okay, so the E field is now given by volt per meter. And it's not just the voltage, it's the change in voltage. And this one has 225 volts on one positive plate and 0 volt on another. So the change in voltage is 225 volts all over the separation distance of 0.03 meters. This gives us a numerical value of 7,500 units. If we just transpose those and bring them over, it's volts per meter. But it's actually asking for the E field, so I'm just going to say it's newtons per coulomb because a volt per meter is a newton per coulomb, but we also need the direction. What's the direction here? Okay, east or right would be fine, yes, because we have to put a little positive charge in here, a positive test charge, and which way would it go? It would go that way. So the direction here is east. Okay, and let's do example number 3. How does the electric field at point X compare with the electric field at point Y? And we're doing it for both A and B. And I guess we're going to have to graph it because we've got the graph set up. So, voltage, here's our rearrangement, our first rearrangement of the formula, equals ED. By the way, is this formula on your formula sheet? E is V over D. Okay? Yeah. So, beware though. This, don't just use it any time. You might want to, on your formula sheet, write down P dot P dot beside it, or parallel plate. That is meant for a uniform E field. You cannot use it any other time. Okay? So we're graphing the Y versus the D here. And so it's kind of like Y equals mx, where E is the slope. And we know that in a parallel plate, the E field is constant. We've just mentioned it and said that it was, because all the lines are the same distance apart. That's another way of taking a look at it, right? When I drew it very first one on the first page, all these lines were the same distance apart. And as we continue on, the distance between the lines are not increasing as we go along the lines. So the density of those E field lines represents that the change of it, and it doesn't change. So the E field at X will be the same as the E field at Y. We get a slope on this graph. It's the same. The E field is the same everywhere. So that's the answer. E field is the same for X and Y. Let's go back to yesterday's and the last 4 days. How does the E field change at X and Y? Well, around a point, this was how we calculated the E field. E was equal to KQ over R squared. Okay, that's how we calculated it. So we're going to use K and Q, but the R is going to be 2 at one point, and then the R is going to be 5 at another point. We've got to square it, and we've got to reciprocate it, because it's under the denominator. So this is 1/4 and 1/25. So definitely it's not going to be the same, and it doesn't change linearly. In fact, it changes as the inverse square. So EX is going to be much bigger than the E at Y. How would this graph look like? Well, this graph is V equals KQ over R, or in this case over D if you want the separation. How does, and this is a constant around that point, K and Q. So how does the graph of Y equals 1 over X look like? Anyone remember that from math? Anyone know what this type of graph is called? Is it a circle? Is it a rectangle? Is it a straight line? Parabola? Rectangular hyperbola? No one knows? Rectangular hyperbola is the answer. Because if you graph it, it looks like that in the first quadrant, and it mirrors it in the third quadrant.
I remember those.
So it graphs like that in the other quadrant. But we can't have a negative distance. Mathematically we can. We can't have a negative distance in a parallel plate. So it looks like that. Definitely the voltage is not constant, and the electric field is definitely not constant. Number 4. Explain why an atom will be ionized, the electron will be separated from the atom, if it is placed in a sufficiently large enough electric field. So we have an atom. It's neutral. It has a positive nucleus, but a negative electron going around it. So the whole atom itself is neutral. And we're putting it in a large electric field. Okay, so the E field is large. What's going to happen to that electron? it's going to feel a force, right? Especially if it's large enough. It's going to feel it going that way. And it will actually move. It'll swing that way, and if it's large enough, it'll fly off. The electron will have a nice velocity over to the left, flying off. If we're talking about air mixture, that's the nitrogen and oxygen that we're breathing right now, about 3 million volts per meter will produce ionization. It might seem like a lot, but this occurs frequently. Okay? We hear it as we pull clothes out of the dryer. The static electricity that we have from, rubbing the clothes together for the last 45 minutes with a lot of heat, as we pull it apart, you'll hear the clothes static. You hear the static. What's happening there is that the volts per meter in that short range, very close to the clothing, is huge. And it'll ionize the air. And you'll see the crackle, combing your cat at night in the dark. You get the same type of thing. Rubbing your feet on the library carpet and getting close to the metal, right? You have a large charge on one finger, and as you bring it close to the metal, you're getting a voltage difference per meter. And as you get closer and closer, you're increasing the electric field. As you increase the electric field, the electrons that you've obviously built up will eventually snap through the air and ionize that air. So, and lightning is a good one of that too. Yes, Alex.
When you hear the sound of your clothes, which is a positive charge and which is a negative charge?
Usually the brown cloths are negative. Just kidding. I don't know. One's going to be charged and the other one's not. It depends on the material.
It's really strange that which molecule will gain the electron is actually random. So
It's not really random. It's from Science 9 when we rub different things together, different materials would easily give up the electron and the other one would not. And by doing so, one becomes positive, one becomes negative, and it's repeatable. So it's not random. Each of these effects is accompanied by light. The light occurs because the ionized electron does not remain free. It quickly falls into an orbit around a neighboring atom, and when the electron does this, some of its energy is converted to light energy. Okay, let's talk about lightning. The bottom of the cloud is charged to 2.5 times 10 to the 8th volts. How close does the cloud need to be to the ground for a lightning bolt to occur? So this is our cloud. Let's draw it in blue. I should have done it in blue. There's my cloud. Why do we have blue clouds? They're white. It's a blue sky. So I'll do white ink here. Just kidding. Okay, and then we're going to have a lightning bolt down to the ground. Okay, and this is the ground. So here's your house and a tree. Okay, so how close does the cloud need to be to the ground? Okay, and for a lightning bolt to occur, the air breaks down at about 3 million volts per meter. Okay, so E equals the voltage, the change in voltage over the distance. So the distance is what we're trying to solve for. Distance is the change in voltage. Well, don't draw that V. I'm going to get corrected on that.
You're doing
over E. And the voltage difference, we're told, is 2.50 times 10 to the 8th volts. That's where I draw that V. And the D, the distance, the separation distance, is what we're trying to figure out. The E electric is 3 million volts per meter. Folks, this is volts per meter. When you see that, try to write it down right away because it might clue you in. Volts per meter? Oh yeah, that's a newtons per coulomb. Oh, that 3 million volts per meter is actually the E field. So that's what you have to do. Train yourself to, when you see these units, you don't, what's volts per meter? I don't know. Oh, it's the E field. So this is 3 million. 3 times 10 to the 6th. What is that distance? Someone plugged it into the calculator yet? .5 e to the 8 divided by 3 e to the 6th, 83 meters. So the cloud has to be relatively close, unless of course there's a lot more voltage that the clouds have built up. So example number 6. Where do you not want to be standing in a lightning storm? At the top of a mountain? Top of a hill? Near an apple tree? How do you like my sailboat on water, eh? Yeah, you don't want to be in a sailboat because you know, with yellow gases permeating from it. But anything that points up to the sky, you want to avoid that. Right? Even if it's an insulator, you kind of want to avoid that. You don't want to climb a tree, you don't want to be sitting underneath the tree. You don't want to be sitting in a boat with a nice metal mass pointing to the sky. But of course, what are you going to do? You're in a boat and a storm happens. You're not going to go jump into the ocean, right? That's a good time to put on your rubber overalls.
But is it safe for you to jump into the ocean?
Is it safe for you? If you stay away from the boat, yeah. Safe, but I wouldn't want to be. I'd rather lay down in the boat.
And you know, there's huge metal rides, huge buildings. My parents like.
Please. Example 7. Find the acceleration of an electron placed between the metal plates that are separated by 2.5 centimeters and charged to 275 volts. Okay, so there's an unhappy electron in there. Why is an electron unhappy? It's negative. Okay, good. Sorry, bad. So we're trying to find the acceleration. Well, we know from yesterday when we went over everything, force QE. And the force is mass times acceleration. So that equals QE. And we can get the E by doing voltage over the separation. This only, again, is for parallel plates. That's not pivot point, but parallel plates. So the E field inside this parallel plates is 275 volts over the separation of 0.025. So the E field in between these two plates is 11,000 newtons per coulomb. or volts per meter, whatever you want. I like newtons per coulomb. So we're now going to take a look at the acceleration. Acceleration is QE all over m. And that means the acceleration is Q, the charge of the electron, 1.6 times 10 to the negative 19th coulombs. E is 11,000 newtons per coulomb. And the mass of the electron is 9.11 times 10 to the negative 31st. So 1.6 e to the negative 19th times 11,000 divided by 9.11 e to the negative 31st. We get a massive acceleration here. 1.93 times 10 to the 15th meters per second squared. Okay? Questions? Yeah. We wouldn't let it happen for very long. It couldn't accelerate at that rate all the way across the 2.5 centimeters. Okay, yeah, good. Which direction does it accelerate? There was a question, why don't we put the negative for the charge up here? Okay, well, remember with the E fields and stuff like that and forces, we just use the logic afterwards. Which way does it accelerate? And will it go up or down? Point to me. Which point? Does it go up or down? Thank you. And for the record, everyone that's listening online, that was up. Yes, you're wrong. So let's talk about the Milliken oil drop experiment. In a very famous experiment to measure the charge of an electron, Milliken used parallel plates to hold an oil drop in place. The drop of oil remained in place because the electric field of the plates balanced the gravitational force down. Okay? Can we do this? Well, we'd have to set it up. The oil drops are small enough that they're atomized, meaning you spray it out of a little bottle, so they're small. You have to have a microscope looking at it. Now it has to be horizontal. You can't look down through a microscope. It has to be horizontally at it. And then you find by atomizing it through the spray bottle, there's friction as it comes out. Some of the oil drops are going to be negatively charged. Some of them are going to be positively charged, depending, I guess. And you put it in between the parallel plates, and then you look at it with the spyglass, with your magnifying glass, with your microscope, and you change the voltage on the plates until the oil drop doesn't go up or down. If there's too much voltage, then there's too much of a force upward. And if there's no voltage, all the oil drops drop because of gravity. They'll eventually fall down, right? So by measuring the size of the oil drop, they can get the mass of the oil drop. And if you know the mass and the charge of the oil drop, I mean, the mass of the oil drop and the voltage on the plates, you could get the charge on the oil drop. Let's go and do that. Let's do that right now with example number 8. So I have this oil drop sitting here in between these charged plates. So the force of gravity is equal to, and that's the force of gravity down, has to balance the electrostatic force up. That when we add them, they actually are equal to 0. So they have to balance. So the force of gravity down, mg, has to equal the electrostatic force up times q, the charge on it. And E is, from today, E is equal to the voltage, the change in voltage over the separation of the plates. That's again for parallel plates only. Okay, so if you plug that in to the V here, we get Q, the change in voltage over the separation. And isolating for Q, we get Q equals mg d over V. I guess I can't draw the V that way, folks. Over the volt. Let's look at example number 9, and then there's the homework there. A particle of mass, there we go. Really small mass, 10 to the negative 14 kilograms, and charged with 3 electrons, is suspended between parallel plates. What is the voltage in the upper plate to keep it charged? Okay? Again, start from the basics. Don't start with this formula that we ended up with. So the electrostatic field has to balance the force of gravity on it. The electrostatic force has to balance the gravitational force. So QE equals mg. I'm going to replace the E with delta V over D because it's parallel plates. We can. And that's a Q, not a G. You just didn't look at it the right way. See, it's Q. Equals mg. And rearranging this formula, we get the voltage is equal to mgd over Q. So we plug in the numbers. The mass is 2.3 times 10 to the negative 14th. Do the numbers, please, for me. Plug it into your calculator. G is 9.8 because we're doing it on the surface of the Earth. The separation between the plates is 0.015 meters. And the charge is 3 times Now, when we calculate it with the negative number in there, we get negative what? 7043 or 44? 44, does it round up? Which, it's negatively charged, which way is it going to go up? I mean, thank you. Which way is it going to go up? Up, very good. It's going to go up. So when you calculate the change in voltage, you will get either a positive or a negative depending on which way you're doing it. If it's balanced, you can do the logic that the higher voltage has to be up because it wants to be attracted to that. Any questions?